Hey everyone, how's it going? My name is Daryl. Welcome back to my channel. Today I'm going to talk about how to reshape input data for long short-term memory network. Often it can be difficult to understand how to prepare your sequence data for input to an LSTM model. There's confusion about how to convert your 1D or 2D matrix to the required 3D format for an Rstm input. Also, often there's a confusion around how to define the input layer for the Rstm model. So in this tutorial, you will learn three things. The first is how to define a LSTM's input layer. And then you will learn how to reshape multi-parallel series data for a Rstm input. And finally, you will learn how to build and train a Rstm model. Ready to go? Let's get started. To make it easy to follow, you can download this notebook from GitHub and follow along with this step-by-step tutorial. The most critical part of this video is to teach you how to reshape the multiple parallel series data that you have for a Rstm input. The Rstm input layer is specified by the input arguments, that is the input shape arguments on the first hidden layer of the network. So in that case, this can make things confusing for beginners. And the inputs to every Rstm layers that has to be three-dimensional, which is unlike what we have with the traditional neural network. The three dimensions of these inputs are including the samples, the time steps, and also the features. This means that the input layer expects a 3D array of data when fitting the models and when making predictions, even if specified dimensions of the arrays contain only a single value or one sample or only one feature. We still need to create it as a 3D shape. So let's learn it by doing. First thing first, let's import the data set. We are going to import the data with the use of pandas. So we're going to import the pandas framework, and at the same time, because we need to work with the 3D array, so which is a ND NumPy array, so we need to import the NumPy framework as well. And in this example, what we're going to do is to download the data from the AEMO, which is the Australia Energy Market Operators. Download the electricity data that includes the price and also the electricity consumptions. So you can actually follow this link to download the data. And then I already download the data and append them month by month. And then you can see that we already have around 1.5 years data. With these data, what we're going to do is to use the electricity demand data and the price data in the previous state to predict what is happening in the next 30 minutes about the price. So to predict the price at 30 minutes later. Now let's take a look on the CSV file first. We have the index columns because I append the data month by month, so I still keep the original index columns for in the column A. And then for the column B, that is for the regions. This is the Victoria regions. And then for the settlements, that is the settlement date and settlement times. And then we have the total demands for that period of times, and then the average price for that period of times. And that is the columns and the data that we have. So the first things that we are going to do is use the pd.read CSV files to read this data into a data frame. And this is the data frame that we just extracted from the CSV file. And let's take a look on the type for each of the columns. And for the index, that is an integer, regions, that is an object, settlement date, that is an object, the total demands and the price are the floating, and then the period types is another object. There are three columns that we're going to use, including the settlement days, total demands, and also the price. And you can see that the settlement days right now is an object types, and total demands and the price are the floating types. So the first thing that we need to do is to convert this settlement date from an object type to a date time object. In that case, what we are going to do is to use the built-in methods, that is two date time methods, to convert these types. The columns that we would like to convert is the df settlement dates, that is the first argument, and then the second argument is that we set the date first equals to true. It means that the first value here is a date, and then followed by month, and then by years. So we set the date first equals to true, and here we assign as a new columns that is called the date time. And then for this one, now because this is a date time object, so we can just convert it. We can just use the date time methods, that is a .dt.day, to extract the day and to extract the month, the years, the hours, and also the minutes. So in total, you can see that there is a 6 additional column shown here that includes the daytime, which is a daytimes objects, the days, the month, the years, the hours, and also the minutes. Now, if we print out the column types, you can see that the daytimes is a daytimes object, and then followed by the integer types for the day, month, years, hours, and minutes. And normally, these total demands and also price might not be the data types that you want. So in that case, you might want to use the two numericals to change the types of these total demands and also the price. And in this case, it's already the right typed, but still, I just want to show you how to convert these object types to a numerical. In that case, we use the to numerical methods, and then the first argument is that is a total is the total demand columns, and then for this one, the first argument is the price column. Here we set the errors equals to coerce. It means that for any missing value, we will just fill it up with NaN. And so we then assign it to a data frame with the new columns called demand and price. And if we take a look on the data types, and now we have the demand and price, that is a numerical data. The next things that I would like to do is to drop out all the columns that are not needed in this data frame, and that includes the index, regions, settlement days, total demands, RRP, period types. So all of them will be dropped out. And now what we have in this data frame, that includes the price, the demands, and also the day, month, years, hours, and minutes. And now we are ready to transform the data. The first things that I would like to do is to create an empty list for each of the features and also the target. And then with this empty list, what we're going to do is to append each of the values into these empty lists. So what I'm doing here is actually like this, is that I take out 48 points, and then I shift one step and another 48 points, and then continues to append to the empty list. So in that case, what we are going to have is that we have a bunch of samples over here. And then for each of the sample, we have 48 points. And this is for the demands columns. And then I'm going to append the dates, the month, the years, the hour, the minutes, the demands, and also the price with similar logic. And so you can see, I just take out all previous 48 steps and then append into each of the and append in each of the row in this or each of the elements in this empty list. And that is for the features. For the target, is like this. So this is 48 steps. So this, let me highlight this for you. This is a 48 steps. So in that case, what I would like to do is to use these 48 steps to predict what is happening in the next 30 minutes. In that case, what we are going to predict is these spot price of the electricity. So and then of course it will continue to shift for each of the steps, for each of the 30 minutes interval. And that is for the label. Let me print out the types of the X5. That is one of the features, that is the demands features. And you can see that it's still a list. And so this is what we got for the X5. This is the list. And then originally is inside a data frame. And now it has been appended, just like what I mentioned before with the use of this for loop. So say for example, it take out the 48 point over here, and then it will shift 1 point for each of the row, for each of the sample. So in that case, you just shift 30 minutes and then store another sample, and it continues until it reaches the end. And now, because this is still a list, so I would like to convert them into a NP array, that is the ND numpy array. So for each of them, I will just use the np.array function methods to convert the list into an array. Now let's take a look on the output shape. This is the output shape. In order for it to work with the training algorithms, we need to expand these output shapes with an additional dimensions over here to make sure it works properly with the training algorithm. So we just need to use these reshape functions and then add one dimensions into these vector. To smooth the trainings, normally we need to normalize the data or standardize the data. And in this case, we are going to use the min-max scalar, and then which provides a range between 0 to 1. And in that case, what we're going to do is to transform all of the features as well as the target with these min-max scalar. So we will first use this min-max scalar and then decide the range that is 0 to 1, and in this case, and then convert it into assign it as a scalar object. And then once we have these scalar objects, what we're going to do is use the fit transform functions for each of the feature. Apply these fit transform functions to each of the features, and then we will just convert, assign it back to the original ND array. And now we have all of them has been scaled scale down between 0 and 1. And now this is the results that we have for one of the features, and this is the demand features. And let's take a look on this shape that is for these demand features. And now we have around 25,000 samples, and then for the sequence, for the time step, we have around 48. The next step is the most important step in order for us to transform it into a 3D format required by the LSTM layer. What we've done here is to use the NumPy stack, that is to stack each of the features into this X array, and then with the access equals to 2. So it means that we are going to stack each of the features along the axis 2. And because at this point we do not have the axis 2, that is 0, 1, and axis 2. In that case, what that means is that we are going to expand these features with new dimensions, with these 7 features. So you can see that the final shape is looks like this. This is the 3D required format for the LSTM models. And now for the first element that contains the sample, and then for the second element that contains the time steps, that is the previous date or the previous 48 time steps for each of 30 minutes interval. And then finally we have the 7 features. So we just finished to reshape the multiple parallel series data for a LSTM input. The next things we're going to do is to build the Rstm model. We just separate the last 10 days for the testing. So here you can see that we assign the X, and it starts from the beginnings to the last 10 days, up to the last 10 days for training, and then the last 10 days will be used for testing. Now, and then we also assign the labels with the similar logic. And you can see that for the X train dog shape, the second dimensions, that is 48, and then the third dimensions, that is 7. And this is the input shape for the LSTM. And now we are ready to use the TensorFlow carrots to build the models. The methods that we are going to use is to use the sequential APIs to build the models layer by layer. So of course we need to import the sequential models, and then for the layers, of course, we need to import the Rstm and also the dense layer. And we also import the optimizers for some parameters tuning. Now we first assign our models as a sequential models. And then what we are going to do is to add 2 Rstm layers and then 2 dense layers. For the first Rstm layers, we assign 50 neurons, and then the return sequence, it need to be set as a true. The reason is because we are going to have another LSTM layer. In that case, we need to set it equals to true. For this one, because we do not have another additional LSTM layers followed by this Rstm layers, we have a dense layer followed by this layer. So in that case, we can set it as false. For this lines of code, because this is the first input layer, so we need to assign the input shapes. Remember that this is the input shape, so we just put input shapes equals to the xtrain.shape dimension 1 and xtrain.shapes dimension 2. This is the input shape. And then now we have this input layer, and the next layer we will add an additional LSTM, and the return sequence equals to false because the next layer will be just a dense layers. And for these dense layers, the activation function is value. And finally, we just add a last layers, which is a the output. That is and the activations is just linear, so we do not need to add that. But with one new ones because the target is a single output. Now, if we let's take a look on the model's summary. So with the input shapes and then go through these LSTM's layer, it will provide these output shapes. Remember, it's because we set the return sequence equals to true, it will return you a 3D output shape for the next LSTM's layer. And then because for the return sequence equals to false for the second LSTM layers, so it will just flatten it and then return you a 2D output result for the next layers. Now we are ready to go for the trainings. Before we feed the data into the sequential models, the first things that we would like to do is to import the model checkpoint and also the early stopping functions to early stop the trainings if there's a if we find that the validation loss is going up. And on the other hand, we also would like to save the models, save the best only models into this path. So once we set this callback and set this file path and set the set up the model checkpoint and early stopping properly, we can then set up the optimizer. In this case, I'm going to use the SGD optimizer, and with momentum equals to 0.9, and so this is the optimizer of SGD, and the loss functions that I'm going to use is MSE, and for the metrics that I would like to monitor is MAE. And finally, we are ready to fit the training data into the models. And I take up 20% of the training data for the validation. And outside the callbacks, as the callbacks that we set over here, and the batch size is 16. And not too long, after around 21 epoch, it will just end the training. And finally, I also use the model.evaluate methods to evaluate with the test set data. And evaluate give us the MSE and also the MAE over here. And finally, we can also use the predict methods to make a predictions on the output. Remember that we just transformed the original data into with the use of the min-max scaler. So in that case, we need to use the same scaler to do the inverse transform of the predictions. So now these are the results after we use the inverse transform scaler. And let's take a look on the plots over here. And from this plot, you can see that the red line is the actual price, actual electricity price, and then the blue line is the forecast price. And in terms of the trends, it actually track it quite well. However, in terms of the spike, you can see that it doesn't follow too much. And if we zoom into this huge spike, and you can see that indeed these forecast value also predict a huge value in this huge spike period. And of course, we can further increase more features and fine-tune the hyperparameters to make a better predictions. But the whole point of this tutorial is to provide you an ideas and templates on how to set up the LSTM's input layers and build a Rstm models from the raw data from the CSV, and then convert it into a 3D shapes that is required format, that is the required format for the Rstm models. So if you have any questions, any further comments, please feel free to leave me the comments and I will do my best to answer. So see you in the next video. Bye bye.